Hey everybody, today we're continuing our conversation about confidence intervals and inference on means. And in order to do so, we have to start a conversation about a brand new curve that we're going to be looking at, which we call the t-distribution. So let's first start with a refresher of what we have done up to this point. So we have focused on confidence intervals and inference on proportions. Now, we should recall that proportions actually come from binomial distributions. We talked about that in class. And binomial distributions are essentially normal for large samples, for large values of n. Because of that, we have been able to use the normal curve, or z-distribution, to do confidence intervals and inference on proportions. You've been using normal CDF and all those wonderful normal functions on the calculator. We have also recently, last week, done confidence intervals for means when the standard deviation of the parent population is actually known to us. When the population had a known standard deviation sigma, the sampling distribution had a standard deviation of sigma divided by the square root of our sample size. We were also able to use the normal curve, or z-distribution, because we somehow magically knew what the standard deviation of the parent was. So, in summation, up to now, everything we have done has used the normal curve, or z-distribution. But unfortunately, the normal curve does not do everything for us in statistics. This was really first investigated by a man named William Gossett, who was a chemist and a statistician. And he was studying the production of barley. And, you know, it's the same type of grain that you might find in your beef barley soup. But he was studying it for a different reason. William Gossett worked for a little company known as Guinness, which is stationed in Dublin, Ireland. And he used statistics in order to do his work. And William Gossett realized through trial and error that when the standard deviation of a parent population is not known, which is almost always the case, using the z-distribution led him to too many false positives. So basically, he was rejecting the null hypothesis too frequently. So in investigation, he ended up realizing that a new curve was needed, so he couldn't use the normal curve for the work he was doing anymore. And this brings us to the curve that we now call the t-distribution. So let's first review how a t-distribution is like the normal curve. Well, like the normal curve, the area underneath it is 1, and this is necessary because it is a probability density curve. Its shape is unimodal and symmetric. And like the normal curve, its mean is 0. So the center of the t-distribution is on 0, just like the normal curve. But obviously it's not the same, so the big question is, how is the t-distribution actually different? Here's the kicker. The t-distribution's exact shape actually changes as your sample size changes. And this is completely new because the normal curve had the exact same shape no matter what the situation was. The change in shape is important because, in general, the t-distribution has more area in its tails as opposed to the center when compared to the normal curve. And the other important piece is that as your sample size increases, the shape of the t-distribution will actually start changing to look more like the normal curve. So let's actually take a look at what the t-distribution really looks like. So what I have here is a depiction of a standard normal curve. It has this traditional bell shape. It's centered at 0. It's unimodal and symmetric. And you can see here, plus or minus 1, this is where our 1 standard deviation away, 2 and 3, and so on. So this should be very familiar to you. But let's introduce a new curve. So the smallest sample you could possibly take in statistics is to have a sample size of 2. If you have any less than that, like a sample size of 1, you can't really do any statistics on it. So the absolute smallest you can go is 2. So when your sample size is 2, this is what the t-distribution looks like. So notice that it's unimodal and symmetric. It's got one maximum here right in the middle, and it is centered at 0 just like the normal curve. But take a look at everything else. Look how large its tails are when compared to that of the normal curve. They're much higher. So there's more area in the ends of the t-distribution when compared to the normal curve than there is in the center. So we can actually change the sample size here and see how it will affect the t-distribution. So our normal curve will not change, the shape of the normal curve never changes, but as I increase the sample size, you're going to see that the shape of the t-distribution will actually start to change. The area in the tails will start going down, the area in the center will start going up, and as that sample size keeps increasing, the t-distribution looks more and more like the normal curve. So here's what it looks like with a sample size of 30. And we can still see the tails are slightly above the tails of the normal curve, but they're pretty close. And the center is still a little below the normal curve, but it's pretty close. And here, the way I've set this, I can go all the way up to a sample size of 100. And you can see at this point, it's almost hard to see the difference between the two curves the way I have this on Desmos. They're still not the same, and technically they'll never be the same no matter how large I make that sample size. The t-distribution will still be a little different, but you should be able to see here that when my sample size gets bigger, the t-distribution starts looking more and more like the normal curve. Now, just a note here, I made it so you could see what my commands here are, and you could see my normal dist command that draws my normal curve, and the tdist command draws my t-curve. And notice what I put inside here. I put n-1. N is the sample size that the curve represents from 2 to 100. But you might be wondering why I put -1. We're actually going to talk about that in the next video for this week. So why does the t-distribution do what we need it to do? Well, it's basically this simple. When we have a lower sample size, the t-distribution, as you saw, will have more area in its tails. More area in its tails means that the t-distribution will give us a higher p-value for our sample statistic, because remember, the p-value is the area that's in the tails of the curve. And a higher p-value makes us less likely to reject the null hypothesis, and that means we're less likely to get a false positive. Nowadays, almost all statistics done on means uses the t-distribution as opposed to the normal curve. So up to now, we have been using the normal curve for statistics on means, and sadly, that's not really how it's typically done because it doesn't work as well. So we use the t-curve instead. Now, what's going to matter to you is how changing the curve from the normal to the t-distribution is going to change your work. First, we're going to be looking at confidence intervals. And the big thing here is that instead of the population standard deviation, because you're not going to know it, you are going to use the sample standard deviation. And that's why we have to use the t-distribution. Instead of using the critical z-star values that we have given you in the past, you are going to need to use a calculator or Desmos to find your own t-star values for each problem based on the sample size. So it's no longer memorizing the 3 numbers we gave you. You're going to have to find them yourself. Later on, we're going to be doing inference on means. And the big change there is instead of using normal CDF to find your p-values, you're going to use TCDF because you're using the t-curve and not the normal curve. So that's not a huge difference there. But TCDF will take an extra argument based on the sample size that you're using, because, again, different sample size, technically different t-curve. So this has been our introduction to the t-distribution, and in the next video, we're going to look at how we actually use the t-distribution to construct confidence intervals for means.